Hello, good afternoon, everybody. So this is Dr. Muhammad Mahmoud. So I want to record this lecture, as I said in my email, and also I want you to watch it. And then if you have any questions in the lecture when we meet, we don't know how long this storm is gonna last, but anyway, when we meet, I will go through the stuff I'm gonna teach right now quickly and see if you have any questions. So as you know from my emails, I have posted chapter 0 and chapter 1. Chapter 0 is just like syllabus and some information about the course. I think I have one student here. Let me ask if he can hear me. Nick, can you hear me, Nick?
Yep.
Yeah, that's good. Anyway, I know it was too late to send email about the online lecture. Because I didn't think about it in the beginning. I thought about recording a lecture, and then I told to myself, as long as I'm gonna teach, why you don't allow students to join anyway. So let me see if the mic is okay. Looks like mic is okay. Okay. So as you know, this course is Introduction to Digital Systems. So I can briefly tell you in this course, you should learn, or we are going to design some hardware circuits that is used in any digital system. When I say digital system, I mean for sure there are different types of digital systems, but the one we use all the times are computers, smartphones. All of these devices are digital systems. Okay. So in this course, I'm going to teach. You should understand when you write your program in any language, C, Java, Python, whatever, at the very end, your program has to be executed by the hardware. Okay. So that's why in this course, that's what I'm teaching this course. I'm going to teaching the hardware, or we're going to design the hardware that is used to mainly to execute the programs. But in this course, I'm not going to teach how can we create a complete system, because this is just, you should learn this in future courses like architecture, to like computer architecture and other courses, but this one just introduction to digital systems. So here I give you some information about me. My name, as I said, Muhammad Mahmoud. This is my office and this is my email. In this course, we have 2 TAs, okay, Mary and Weston PP. They mainly are going to help you on labs and also grading project and so on. As you know, our lectures are Tuesdays and Thursdays from 12 to 1:15. This will be in Brunner Hall, 119. Labs are going to be in Brown Hall, 407. So all the course materials will be posted on iLearn. If you have for office hour, if you need any help, just send me an email. All lectures, not only this lecture because classes are canceled, but all lecture during the whole semester are going to be recorded and posted on iLearn. Okay. I think I found from my experience, I found this is very useful to students, just in case if you missed a lecture for any reason, or you attended a lecture but you missed one part, or you want to listen to the lecture again. I think this is very useful to students anyway. So I'm going to record all lectures, okay, even the ones that are in person, and then post all of them. However, you have to, I'm going to take the attendance, and you have to attend all lectures. Yeah, because the bad side of recording lectures is that some students may think they don't need to attend the lectures. I'm going to take the attendance. You have to attend all lectures. Here, this is a description description of the course. Okay, so I'm going to leave it just for you to read. In this course, we are going to use this textbook. Okay. However, in my opinion, if you want to buy it, that's okay. But the slides should be enough. The material I'm going to post on iLearn should be enough for you to learn the course. So you may not need to buy it. For homework, I'm going to use Zybox. Okay, so I'm going to send you some information about Zybox, about the code. The subscription last year was 64. Last semester, hopefully it will be the same. I'm going to send you more information about that. We're going to use Zybox mainly for homework. Okay, this is a course evaluation. We have here homework. The homework will be through Zybox, as I told you. It will be 15%. We're going to have one project, which is 10%. For project, it can be done individually, or you can work in group of 2 students. For labs are going to be 25% of the final grade. And for labs, usually students work in groups of 2. Okay, and usually this is the normal case. The group of labs are the same groups for project. Okay, so during labs, every group has 2 students. You can work together. When you do the project, usually it's the same 2 students do the project. Okay, some students like to work individually. I don't mind. I don't have any problem with that. Although still team working is important, but anyway, if you prefer to work alone, I don't mind. But usually the normal case is 2 students in each group. We're going to have several quizzes, 15%. We're going to have 2 tests, 15%. Final exam is 20%. If you add everything together, you find it is 100%. Okay. For the students who are attending right now, I'm okay if you want to interrupt me and ask me any question. That's totally fine. Yeah, so here I'm going to use the standard way for the grades. So in order to get A, it should be between 90 and 100%, B between 80, 90, and so on. So this is a normal one. For sure, I don't need to say any academic misconduct is not be tolerated. Yeah, so here I just, in the last 2 slides here, I give you some advice. If you want to do well in this course, what should you do? Okay, I'm going to tell you something very important in this course. You know, some classes they are separate topics. Okay, so if you miss one chapter, it may be okay. You can still continue working with the course. However, this is not the nature of this course. So in this course, what I'm going to teach today, I'm going to use it in the last lecture. You understand what I'm saying? So it's just one unit. Okay, so that's why if you miss if you don't understand one part of it may be in this course, it may be a problem for you in the future. It's just how it is. This is the nature of this course. I wish if you can do homework labs by yourself. If you just copy from someone else, or if you just depend on your partner to do the labs and without understanding them, this would be a problem, because you are not going to be able to solve quizzes or exams, questions of the okay. One more thing, which is very important. Unfortunately, this is bad. So, but I need to tell you about it. So what happens here in last semester, some students, okay, so usually students get very high grades in labs, okay? Some students do very well in quizzes, usually, okay? Also, maybe, yeah, also good in tests. So after that, you think you already guarantee very high grade in the course, and you don't care about homework. Homework is 15%. So last semester, one student who failed this course because mainly he for sure, in addition to other things, he didn't do anything in the homework. Okay, it's 15%. So you need to do the homework, it's 15%. Also, you need to do well in the final exam, it's a 20%. So I just want to tell you that if you get full mark in all labs, that doesn't mean you guarantee A in this course at the end, okay? Unless you understand these labs, okay? Because there are other things you have to do. You have to do the homework, you have to do well in the final exam in order to get A, okay? So this is my advice to you. Don't just, you have to do everything here. It's 15%. If you don't do it, and for sure you are not going to do well in some parts here, you may not pass this course, or you might not get good grade. Okay. Anyway, I think that's all what I have here. I can say. Any questions? If you have any questions, that's okay. Okay. I have posted chapter 1 and chapter 2. So I'm going to start with chapter 1 now. We make this one bigger here. Okay. Yeah. So this chapter here, I'm going to talk about binary. I'm going to talk about different number systems. Okay. So here, you know, in our life, the system we're using for numbers, we call it decimal numbers. That's what we are using in our life. Okay. The decimal numbers we are using in our daily life, we have digits. We are using digit from 0 to 9 to represent any numbers. We use digit from 0 to 9. And this system, this system is called decimal, okay? And the base is 10. The base is 10 means we have 10 numbers here, okay? So any number, it should have digits from these 10 numbers, okay? There are other systems we don't use in our life, but they are important in this course. For sure, I'm going to tell you why we need to study them. For example, here, I'm going to teach binary numbers, okay? In binary numbers, the base is 2, which means we have 2 digits, either 0 or 1. So any number is going to be represented using these 2 digits, 0 and 1, okay? That's called binary number. We have also octal number. Octal number, the base is 8. So that means we have here 8 digits from 0 to 7. So any number can be represented using these 8 digits, okay? In hexadecimal numbers, okay? By the way, octal means 8, right? Binary means 2. So decimal, I think, means 10, okay? So it's 10. So it's referring to the base. Hexadecimal means 16, okay? So here the base is 16, which means, okay, we have 16 digits. Any number can be represented using these digits. So in this digit, we have here in the base, okay, let me write something here. Yeah. So here, this is the base 16. So that means we have numbers from 0 until 15. From 0 to 15, we have 16 digits. However, we have here until 9. So from 0 to 9. And then 10 is going to be represented by A. 11 is going to be represented by B. 12 represented by C. All the way until 15, it is represented by F. So that's why, as you see here, the digits in the hexadecimal numbers are actually from 0 to 9, okay? And then from A, B, C, D, E, F. Any number can be represented using these digits, okay? So let me see. I think that's so. Now, one of the things we should understand is, for example, if I tell you 10, okay, this number, it's a valid number for decimal, which means 10. This is a valid number for binary, which means, as I'm going to explain later, this is 2. So, okay, if I have 2 apples, okay, so this one is valid for this one, which means 8. This one is valid here, means 16. So the problem is, if I just tell you 10 here, how can you tell if this number is decimal or binary or octal or hexadecimal? How can you tell? Is that something you can guess? The answer is simply no. You can't guess. You have to tell me. Okay. That is why usually what we do, we open parentheses this way, and I put 10, and then I put here, for example, 2. So if I put here 2, that means I'm telling you this number in binary. Or I can put here 8 to tell you this is octal. Or I can put 10 here, okay? This is how, or I can put 16. This is how I can tell you if this number, the system of this number, okay? That's what I'm explaining here, okay? So any number, usually I have to tell you what is, because it's not something you can guess, okay? Because the same number can be valid, okay? Some numbers, like for example, 3A. This number, you can guess that this number is hexadecimal, okay? Because it can't be octal, because octal doesn't have E. It can't be binary. It can't be decimal, okay? However, some numbers you can't guess, okay? Like, for example, as I told you, 100, for example, okay? Something like that. This is valid for all systems. You can't guess, okay? So now, let me conclude what I said. For numbers, we have different systems, okay? To represent numbers. I explained the digit we are using. I explain how can we differentiate, how can you know if this number in binary or octal, whatever. So now I want to answer question. The question is, why we need all these numbers? Why? I'm going to tell you simply why. Simply because in any digital, the word digital system or binary system, we use these binary numbers, 0 and 1s. I think maybe you already heard something like that. Computers can only use binary number 0 and 1s. Okay, everything we transmit over the internet is binary, 0 and 1s. Okay, your files, the files stored in your computers are 0 and everything is 0 and 1s. Okay, even you do some operation like addition, subtraction, whatever you do it by the microprocessor, everything is 0 and 1s. Okay, so yes, hello. Any question? Any questions? Can you mute your mic? Let me mute you. Okay. So any number here can be that's why this system is used by computers. This is used by human. Okay, we use these numbers. Okay, that's why this system is important. That's why this system is important. Okay, but at least you understand now everything I'm going to teach in this course is just 0 and 1s. Hardware, any operation hardware can do multiplication, addition, any other operation as I'm going to teach in this course. All of them are in binary. So if this is the case, why we need these two systems? Okay, you will understand later the reason computers don't use these systems. Okay, however, because binary numbers are very difficult for us. It's not convenient for us to use binary numbers as humans. Okay, it will be more convenient to use hexadecimal, okay, to refer to binary numbers, because it's easy to convert, as I'm going to teach later in details. It's easy to convert hexadecimal to binary. For example, if I have a number like something like that, 1 1 1 0 1 0 1 0 whatever 0 1 whatever. Okay, so it's very difficult to remember this number. If I tell you the memory location is storing this number 0 0 1 0 1 0, it's inconvenient for us to use it this way. Okay, that's why what we do, as I'm going to explain later, usually I'm gonna tell you the memory location is storing here. We take 1 to every 4. Okay, sorry, let me delete it. So for example here 1 1 0 0 1 1 1 1 0 1 0 1, whatever it is. Okay, so instead of giving this number, telling you the memory is storing this number, usually it's more convenient for us to use hexadecimal. Why? As I'm going to teach later, what happens here in hexadecimal, every 4 digits are going to be represented by only 1 digit in hexadecimal. So this one will be represented by 3. This one is actually F. This one is, let me check, 1 2 4 8. So this is 12. This one is 12. 12 is A, B, C, D. So 10, 11, 12. Is that right? So it's C. So C. So which one is easier for us? Which one is more convenient to tell you CF3, or it's more convenient to tell you 1 0 1 0 1 0? No, this one is more convenient for us. So conclusion, binary is used by computers and hardware. Decimal, this is the number we are using. However, if I want to tell you some binary numbers, okay, I'm going to use hexadecimal or octal. But actually, to be honest with you, most of the time we use hexadecimal. We don't use octal that often, but most of the time we use hexadecimal. Okay, so it's more convenient to use hexadecimal. Just to tell you, CF3. Okay, and once you have this one, it's easy to convert it to binary. Okay, that's it. But hardware is not using it. Okay, just maybe more convenient to represent binary number using hexadecimal than binary. They're almost the same, because if you have this one, it's easy to convert to here or here. I'm going to give you more details in this one anyway. So now I'm going to what I'm teaching right now is how can you convert between different systems. Okay, so if you have a number in binary, in decimal, how can you convert it to binary, from binary to hexadecimal, and so on? How can you do these conversions? That's what I'm going to explain. So what I'm going to explain now is how can you convert any base to decimal. Okay, any base here, I mean binary or octal or hexadecimal. How can you use it to decimal? And you will find something interesting here. The way we are going to do this conversion, it's the same. It's the same if it is octal or binary or hexadecimal. We just change the base. That's it, as you will see right now. So it's almost the same technique. Okay, so let's do it. So first of all, if you want to convert any base to decimal, so I'm going to start with the conversion of binary to decimal. Okay, so if you have this binary number, the approach is very easy. Look here, and this is valid for any base. Okay, so look here, let's read this one. To convert any number, any base to decimal is done by multiplying. You have to multiply each digit by its weight and do summation. Okay. So let's see. So for example, if you have a number this way, okay, every digit here has a weight. Okay, what do you mean by weight? I'm going to tell you what I mean by weight. For example, let's go to the decimal number, the number we are using in our life. Like for example, 275. This is the number. You know that this one is one in ones, this one in tens, and this one in hundreds. That's what you know, right? Because this is exactly what we call a weight. So the weight of this one is 10 to the power of 0, which is 1. The weight of this one, 10 to the power 1, which is 10. So any number here is in tens. This is how many number of tens. This one is actually 10 to the power of 2, and so on. Okay. So that's what I mean by the weight. The weight here is not the same like weight here. It's not the same like the weight here. Okay. By the way, we're going to use the same approach for the other bases, but the only difference is because this system is decimal, here we put 10. If it is binary, I put 2. If it is octal, you put 8. You just change the base. Okay. So that's exactly what I'm going to do right now. So all what you have to do is every number here has a weight. Okay. Similar to the weights we have in decimal numbers. So this number, okay, the weight of this one, 2 to the power of 0. This one is actually 2 to the power of 1. This one is 2 to the power of 2. This one is 2 to the power of 3 and 2 to the power of 5 and so on. Okay. What again? So this one has the least weight. The last one here has the most weight, big weight. This is exactly the same thing when I say 3,720 or 21. So this one is 1, but this 3 is actually 3,000. Okay. Anyway, it's the same thing. All what you have to do here, guys, is to convert this binary number to decimal. I'm going to multiply every digit here by the weight. So this is 1. I'm going to multiply it by 2 to the power of 0. And then here 1 multiplied by 2 to the power of 1. For sure, if it is 0, you don't need to waste your time in the multiplication because 0 times anything is 0, right? This one is 1. 2 to the power of 3, 2 to the power of 4, 5, 6, and so on. Once you do that, once you multiply every digit here, 1 or 0, okay, multiplied by the weight, you just add the result together, and this will be the result in decimal. Okay, so this number in binary is equivalent to 219 in decimal. Okay, any questions here? Okay, so if this number in binary, but what if this number in other base? Everything, I'm going to repeat everything again. The only difference is I'm going to change the base here. Okay, I'm going to change the base. So in case of octal, I'm going to put 16. In case of hexadecimal, the base is 16. In case of octal, I'm going to put 8. That's it, and everything is the same. That's why I'm telling you it's interesting, because it's just the same approach. That's what I'm going to do now. But before I do it, before I move forward, I want to now to tell you about if there is a point, here. By the way, in this course, most of the time we're not going to use a point, okay? But just to explain everything, if there is a point, how can we do it? For this part, that's what I explained here. This is the part at the left of the point. Okay, so this is the integer part here. Okay, so here you multiply. It's again everything almost the same. However, what comes after the decimal or after the point here is the weight. Look here, the weight is 2 to the power 0, 2 to the power 1, 2 to the power 2, 3, and so on. This is anything to the left of the point, but to the right of the point here, because this fraction. So actually here the weight is 2 to the power of -1, -2, -3, -4, and so on. Okay, and that's it. Again, you are gonna multiply the weight by the numbers. So I multiply this one by this one, I got 8. Multiply this one, got 4, got 0, got 1, and then I'm gonna add every here also. Okay, I get this one, and then add everything together. That's how can you convert it to decimal numbers. Okay, yeah. So here it's also the same thing. Here you have 0, so but you have this part here. So again, I'm gonna multiply this one by the weight, but the weight here is 2 to the power -1, -2, -3, and so on. So as you see here. Okay, any questions? Again, just I wanna teach everything, but this I don't think this coursework can use this binary point. Now I'm going to teach how can you convert octal to decimal. Again, it's exactly the same thing. So if I tell you this number in octal, okay, again, this is not something you can guess. I have to tell you this is in octal, okay? Or I can put parentheses here and tell you this is octal 8, okay? That's what I did here. So now, how can you convert this one to decimal? Very easy. It's the same approach I have just explained now. You have to multiply every digit by the weight, its weight. So what are the weights now? The weights is similar to what I explained before, but this one should be 8 to the power of 0, which is 1, right? 8 to the power of 1, 8 to the power of 2. That's it. And then multiply every digit by the weight, add everything together. By this way, 140 in octal is actually equivalent to 96 in decimal. Okay. Any questions? Okay. Same thing for the fraction. If you have a fraction, it's exactly the same thing. So anything again you have to multiply even number by the weight, add everything together. However, anything after the decimal point to the left, the weights here 8 to the power of 0, 1, 2, and 3, 4, 5, 6, and so on. But what comes here actually is -1, -2, -3, -4, 3, 4, 5, and so on. Okay? Then add everything together. That means this number in octal is equivalent to this number in binary. In decimal. Now I'm gonna use hexadecimal. Okay. As I told you before, in hexadecimal we have numbers from 0 to 9, and then for 10 I'm gonna use A for 10. I'm gonna use B for 11. C for 12, G, E, and F. Okay. By this way, you have 16 digits. So again, it's exactly same approach. Again, you have to multiply every digit by the weight. Okay. So this is the weight here is 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3, and so on. By the way, don't be confused. Sometimes you use uppercase like these ones. And sometimes we use lowercase. It's not a big deal. Although I think most of the people are using uppercase, but it doesn't mean anything. Okay, but I think most of the people use uppercase, but there is no difference actually. Okay, so here I give you this number. So all what I'm gonna do, I'm gonna multiply this B, which is 11. B means 11. I'm gonna multiply it by 16 to the weight, 16 to power of 0, 9. 16 to the power of 1, C 12, which is 16 to the power of 2, and then 16 to the power of 3, and then add everything together. By this way, this number in hexadecimal is equivalent to this number in decimal. Okay, it's the same approach. I just change the weight, and when I change the weight, actually I change the base, this base. Okay, let's see. Yeah, now it's the same thing. If you have fraction, how can you deal it with if you have fraction? So again, it's exactly the same thing as I explained before. Here you have to multiply everyone here by the weight, and the weights here are 16 to the power of 0, 16 to the power of 1, 2, 3, and so on. But what comes before the point here is actually this one is 16 to -1, 16 of -2, 16 of -3 if you have more items, okay, and more digits. And then after you multiply every number by the weight, and you be careful here. C actually is 12, so I have to multiply 12. A is actually 10, so I have to multiply 10 by the weight, 10 by the weight. Then add everything together, so you will get the result here, whatever the, yeah, so it multiplies by the weight, and so this number, that's why you can see here, yeah, This number in hexadecimal is equivalent to this number in decimal. Okay. Now I'm gonna explain how can you convert decimal to any base. Again, any base here means because we are addressing binary or octal or hexadecimal. Okay. Also, the interesting part right now is you will find it's also the same approach. You will see right now it's the same approach. We're going to use the same approach. However, similar to what I did here, okay, it's the same approach, but I'm going to change the base, okay? Here I'm going to use 2, here I'm going to use 8, here I'm going to use 16, as you will see right now. So let's start with, maybe you're somehow familiar with something like that. If I want to convert the binary to decimal, so here, instead of using multiplication, as I used to before in the conversion here, when I converted any base to decimal, okay, I used multiplication, I just multiply by the weight. Now I'm going to use division, okay? So here, you have to divide by the base, okay, and everything you get a remainder. You get a remainder here. So you have, okay, let me explain it better. So here, for example, I want to convert 47, okay, so to 47 is in decimal. I want to convert it to binary. So here I'm going to divide it by the base. When I divide by the base, there are quotient and there are remainder. Okay. So then I'm going to take the quotient again, divided by 2, get quotient and the remainder. Okay, I'm going to continue this way, and actually until I get 0 here. Once you get 0, you stop. Okay, so here these remainders are making the binary number. Okay, but let me just remind you what do you mean by division. When you divide, you are going to get when you divide, you are going to get quotient and you are going to get remainder. What this means, I'm going to tell you what it means. For example, look here, guys. So when I divide 5 by 2, yeah, most of the time we say it's 2.5. Okay, yeah, this is one way to calculate it this way. However, there is another way. The other way is if you say here 5 divided by 2, so the quotient is 2, remainder is 1. Okay, so what this means and how can you get it? Okay, very easy. Look here, you have 5. For example, I have here 5, 1, 2, 3, 4, 5. This 5 here. So here I want to make group of 2 because I divide by 2. So this is one group. This is second group. So how many groups of 2 you can make? That's what we call a quotient. So the quotient means how many groups of 2 because you divide by 2. Okay, so now. So what this means? It means I have 2 groups of 2, right? And then the remainder, that's why it's called the remainder. Remainder means the remaining item, which is not big enough to make a group. It's not big enough to make a group. That is why always the remainder has to be less than this number. It doesn't make sense the remainder to be 2. It doesn't make sense. Okay, because if it is 2, it has to be added here to the quotient. Okay, so always the remainder has to be less than this number, whatever the number you are using here. Okay, so that's why in our case here, because you divide by 2, always the remainder is either 0 or 1. Okay, what if I divide by 8? As I'm going to explain later, if I divide by 8, so the remainder should be from 0 to 7. Okay, or I divide by 16, the remainder, because the remainder means it's less than a group, So are making group of 8 if we divide by 8. If I divide by 16, so it should be from 0 to 15, okay? Okay, so let's see how it works here. As I told you, by the way, it's the same approach I'm using right now. I'm going to use it in octal and hexadecimal, but I'm going to change the base. That's it. So here it's 47 divided by 2. So the quotient is 23. That means we have 23, okay, groups. Every group has 2. That means this 23 is actually 23 times 2, okay, which is 46. So the remainder from 47 is 1. That's why the remainder here is 1. And then I'm going to get this quotient here, divide it again by 2. And then see what is the remainder. Get the quotient divided by 2. Okay. This is the remainder. This one divided by 2. And so on. Keep doing it until it is 0. Okay. Once it is 0, you stop here. Okay. So, and now the binary number is actually is actually the remainder you get here. But the part that may confuse you, what is the order? Which one should be to the right? So actually the first one you get is actually the least significant one, or the one that's come to the right here. So you are going to get the number from the right to the left. It's very important, because if you switch it, you are going to have a different number. You get what I'm saying? So the last one you get is actually the one on the leftmost, okay, digit. So the rightmost digit is actually what you get first. So what you get first should be put here first, from right to left. Okay, I give you another example here, so you can just see how we made it. You can practice. Okay, so here I just want to make a definition, because we are going to use this definition all the time. We use the definition least significant digit, okay, or sometimes we call it least significant bit. In case of binary, we call it least significant bit, most significant bit, okay, or digit, whatever. So you can tell from the English name why this one is the least significant and why this one is the most significant, okay? So if you have a number like this one, the one on the right here, the first one at the right, which is the rightmost digit, this one is called least significant, okay? And the one at the leftmost digit, we call it the most significant, okay? Here, I'm going to use this term all the time. You should be familiar with it. Least significant bit, LSB. So LSB, least significant bit. I mean this bit. The most significant bit, I mean this bit. Just a definition. So in the future, if I say least significant bit, you should understand what I mean. When I say most significant bit, you should to make it easy for you. So why this one is least significant and why this one is the most significant? Because of the weight. So this one actually here has the least weight, which is 2 to the power of 0. This one has the most weight, which is 2 to the power. So this one is more significant, more important than this one. Okay. Any questions? So here, I just want you to be familiar with, I'm going to use it all the time. Least significant bit, most significant bit. Again, we use the word bit in case of binary, but you can use the word digit, least significant digit or most significant digit, okay, in any other systems, okay. So now I'm going to talk about, I explain if you have an integer number without a decimal point, how can you convert it to binary? So now I'm going to tell you, if although most of the time in this course we're not gonna use floating numbers, but just to finish or to explain everything, I'm explaining it here. So here, look here how this number here in binary, in decimal, how I convert it to binary. Okay, so actually I'm gonna what we do here is I'm gonna convert this part here, the integer part here, and the part that's after the decimal separately. They are going to be separate. Okay, so I'm going to show you how. So let's start with here, with, for example, 85. Okay, so I'm going to do this part first, 85. So 85, similar to what I just explained. You divide by 2, take the remainder, divide by 2, take the remainder, and the one you get here is actually the one here, the least significant bit. And then this will be the part here. So they are separate. So I finished the integer part, similar to what I explained. Now, let's do the fraction part here, and then put it here. So we do it separate. So let's see how can we do the fraction part. So this is 85. I take the integer part first. Okay. For the fraction here, instead of dividing by 2, we actually multiply by 2. Okay. And again, everything I'm explaining here, guys, I'm going to repeat it again in case of octal and hexadecimal, but instead of using 2, I'm going to use 8 in case of octal. I'm going to use 16 in case of hexadecimal. Okay. So now I want to convert this part. Okay. The fraction part here, which comes after the point. So actually what we do here, as you see, I multiplied by 2. After you multiply by 2, what you are going to get here is either 0 or 1. 0 or 1. Okay. So, and this is actually this is the conversion we are going to use. So after I multiply by 2, I got this part. So I take this part again here, as you see here, multiply again by 2. So I got this one. Okay. And then I take this part, the fraction part, multiplied by 2. Okay. So, and then this is what I'm getting, 0, 1, 1. But again, What is the order? How can you order it? Okay, again, what you are going to get, yeah, it's going to be the first one you have here. Similar to when you divide. So when you divide, if you have a decimal point this way, so when you divide, I'm going to get them this way. When you multiply for the fraction part, I'm going to get them this way, okay? So here I'm going to put 0, 1, 1. Okay, and then I'm gonna put, so I did 85 alone, I did 0.375 alone, and then I'm gonna merge them together to get this number. But now the question is, because one student emailed me about asking about this one, when you have to stop here, okay? In case of division, you have to stop when the quotient is 0, okay? Because if you divide it by 0, you are gonna keep getting zeros, which doesn't make any sense. So I'm gonna put zeros on the left. You know, zeros on the left, it doesn't have any value. Okay, so once you get 0, stop. You are not going to get any numbers again. Okay, here I'm going to stop again when I get 0. Okay, so as you see here, I got 0 here in the fraction part here. I got 0. In this case, I'm going to stop. But sometimes you don't get 0. Sometimes, you know, when you have like 3.7215, it's maybe very big one or infinite number and so on. In this case, if this is, so again, what I'm saying is, it's not always it's going to be, it's not going to terminate always, okay? Sometimes you have a very big number or infinite number, repeating number, something like that. So you can just stop, you can just get 3 digits. It depends on the precision. It's enough to get 2 or 3 digits. That's enough. You don't need to get more than that. You understand what I'm saying? So if it does not stop with you like this case, it's enough to just get 3 or no more than that, okay? So I give you another example here. It's here. This is for octal. So you will see everything will be almost the same. Okay. So here we have 165. Okay, as you see here, I'm going to repeat everything I explained before, but this time I'm going to divide by 8. So when you divide by 8, the remainder you will get is actually a number from 0 to 7. So here I got 5. And the quotient is 20. So I'm going to divide it again by 8. Remainder is 4. Okay, the quotient is 2. Okay, when you divide 2 by 8, the quotient is 0, remainder is 2, right? Because I don't have enough here to make a group of 8. Okay, so, and again, similar to what we did before. So here, these remainder are going to be the number here, and the first one I get them right to left. Similar to the binary case. Okay, here, if you have a fraction, it's exactly the same thing as I explained before. You multiply it by 8. However, when you multiply it by 8, the number you will get here is actually it's going to be a number from 0 to 7. And this will be, this will be the answer here, okay? So, and then you get this one multiplied by 8. You get this one multiplied by 8. You get this one multiplied by 8, and so on. So what I did here, I got this is fraction part, so I'm going to multiply it by 8, okay? So now I'm going to get 2. And 2, if you have decimal point here, so what you are going to get numbers this way. So that's why I got 2 here. Then I got this number here, I put it here without the 2, and then multiplied by 8. So now I got 5. You can see here I'm getting the numbers from left to right. Okay. Yeah. So now, yeah. So why I stopped here? Because it's enough. I already have enough. It's that's why I'm saying approximately. Okay, because I didn't complete. I don't want a very big number. So approximately, you know, any number after that should be not very significant. Okay, because so now it didn't end here. In this case, it did not end because I didn't get 0 here. It is possible to get more numbers, but just 3 numbers should be enough. 2 numbers should be enough. No more than should be enough. Okay. I give you another example here just to learn more. I give you here this example. As I told you, you are gonna convert this one alone. You are gonna convert this one alone. Here I converted this one divided by 8. So I got this number here 5 and then 3. So it has to be 5 and 3 because if you have decimal, I get them this way. Here I get them this way. Okay, you can see here in this example, I get the fraction part. I multiply by 8, multiplied by 8. So I got 2 and then 0.4 multiplied by 8. Okay, and then here I can just stop, okay, and it started to repeat again. It's just if you can get 3 digits, that's more than enough, okay. If here I explain decimal to hexadecimal, everything similar to what I explained before. The only difference now, when you divide, I'm going to divide by 16. And when I divide by 16, the remainder should be a number from 0 until 15. Is that okay? But remember, we don't have 10, we don't write it 10 this way. 10 means A. Okay. So that means you are going to get from 0 to 9 and then A until F. Okay. So that's what I did here. I divided this number by 16. This is the quotient and the remainder is 10. So I'm going to replace because 10 is not a digit. It's not a valid digit in hexadecimal. So I have to convert it to A. Okay. Then I got the quotient divided again by 16. Quotient 21. Remainder is 0. 21 divided by 16, 1. Okay. Quotient is 1. Remainder is 0. Okay. 1 divided by 16. Quotient is 0. Remainder is 1. And again, the way I'm going to write these numbers is this one should come here right to left. So it's going to be A051. Okay. So this one is equivalent to this. Now I am going to take this part, the fraction part. It's exactly same thing as I explained before. Okay. So here you multiply by 16. When you multiply by 16, the number you will get here is actual number from 0 to 15. Okay. So here I got 13. 13 is actually G. And then I'm going to take this part here, as you see, multiply by 16 again. I got 15, which is F. Take this one again, multiply by 16, and so on. So here you got 3. And then again, if you have decimal point, so the number I'm going to get this way. So I got D first, so it should be GF3. Okay. Yeah. Any questions? Okay.
So as
Yes,
you're
sure.
going to as you're going through the like converting between bases, would it be like as you go to like multiple paths, just like the first conversion that you lose accuracy from your original number? Because it's just a bunch of like approximations.
Yeah, this is in case of fraction. So in this course, most of the time we're going to use decimal point. You got what I'm saying? So
Yep.
yeah. So sometimes you don't lose. I think in one example here, yeah. So in this example here, I didn't lose precision or accuracy because it stopped with you. Okay. But in some cases here, I had to stop. That's why here in this slide, I'm saying, let me move this one. So that's why you see in this slide, I said this one is approximately this one. Okay, approximation, because I stopped here but there should be other digit. But you know, these digits are not that important. Okay, this is like rounding when you do rounding or something like that. You got what I'm saying?
Yeah. So for this class, it would be fine. Just go to 3 decimal places for approximation.
Yeah, but for this class, I'm not gonna teach. It's enough. I'm gonna only use the integer part. Okay, I'm not gonna use fraction, but just because I want to cover the topic completely, I'm just explaining also fraction. Okay, but yes, for this class, I'm gonna use only integer numbers. Okay. Yeah, thanks for this question. So now I'm going to teach how can you now. So here, any base to decimal to any base. Okay. So now, what if I want to convert between octal, hexadecimal to binary directly without going through decimal? Okay. How can we do that? And as I told you in the very beginning, if you remember, the reason I'm explaining octal to hexadecimal, because if I want to give you a binary number, it's easy for me to give you it in hexadecimal instead of giving it you in binary, because converting hexadecimal to binary is easy. You got what I'm saying? So, and it's short representation, because as you will see right now, every digit in hexadecimal is going to be represented by 4 digits in binary. Okay. So let's see how it works. Now I want to convert binary to hexadecimal. How I can do it? Very simple. All what you have to do, you have to come from right to left. And then you have to make group of 4 digits. 1, 2, 3, 4. This is one group. One group. Now we have 1, 1. So I'm going to add 0, 0 to make another group here. Okay. So I have here, so now I have 4 groups. Okay. And then you have here four binary numbers. Okay, so this actually, if you look at this, actually is going to take numbers from 0, 1, 2 until 15. You get what I'm saying? So all what you have to do is you have to convert every 4 digit, okay, to 1 digit in hexadecimal, as you see here. So if it is 4 zeros, so I'm going to convert to hexadecimal of 0, 1, 2, 3, 4. So actually what you have to do here, just to make it easy, when you convert this binary number to decimal, okay, for example, this is 8. If I convert it to decimal, this is 2 and this is 8. 8 plus 2 is 10, which is 8. You got what I'm saying? 8. You got what I'm saying? So again, if you have 3-bit, if you have 4-bit number, this 4-bit number can have numbers from 0 until 15. Okay, so all what you have to do is, number one, you have to create right to left, you have to create groups of 4, okay, 4 bits, and then every 4-bit you have to convert it to 1 digit in hexadecimal. So this one is B, because you can look at the table, but instead of looking at the table, this one is 1, 2, 4, 4, 8. So we don't have 4 here because it's 0. So 8 plus 2 plus 1 is actually 11. 11 is B, right? So here B is actually 11. Okay, let's look at this one. 1, 2, 4. 1 plus 2 plus 4 is 7. So this one is 7. Okay, that's it. So this one, 1, 2, 4, 8. 4 and 8 is 12. 12 is actually C. Okay, this is number one. Okay, that's it. So very easy. That's why, again, that's why you are using hexadecimal, because it's easy for me as a human being. It's easy for me to remember this number 1C7B, then remembering this number 1110110. It's difficult. Okay. Anyway, so just and also it's easy to convert binary to hexadecimal, hexadecimal to binary. That's why in this course I can tell you, in the memory you are storing the number 3A. Okay. Actually, we are not storing the number in hexadecimal. The number is stored in binary, but I want to represent the binary to hexadecimal because it's just easy for me. So actually, it's not stored 3A. It's stored 3A, but in binary. Okay, but I'm going to give you the number in hexadecimal because just it's more convenient for me and easy to convert hexadecimal to binary, binary to hexadecimal. Okay, so yeah, so here. Yeah, so here, another example here, I give you another example. I go this way, make group of 4, and that's it, okay? I give you also example for decimal point. In decimal point, so here, what is after the decimal point here, so you have to make groups this way of 4. Same thing here, you have to make group of 4, but this way, okay? And that's exactly what I did. So what I did here, this is group of 4. This is 3, less than 4, so I'm going to put 0 here to make it 4. This is 3, so I'm going to put here 0 to make it 4. And then this number 0, 1, 1, 1, 0, 1, 2, 4, which is 6. This is number 6. Okay, when you convert it, it is 6. This is C, this is 4. That's it. Okay, so again, if you have here decimal point this way, okay, and you have a binary number, if you have a binary number, you have to go this way to make group of 4. Then you have to make it go this way to make group of 4, and every group of 4 you need to represent it using only 1 digit. Okay. The next one here is actually how can you convert hexadecimal to binary? It's very easy. All what I'm going to do, I'm going to do the opposite now. That's it, the opposite. Okay. So every digit here, so this number is in hexadecimal. Every digit here, when I convert it to binary, has to be represented in 4 bits. 4 bits. Okay. So remember, C is actually 12. And for 4 bits, 12 is actually 8 and 4. 8 plus 4 is 12, right? So it has to be 1100. Okay. This number is number 2. Okay. So which is 0010 this way. Okay. This number 2. Okay. In 4 bits. 1, this is 1 in 4 bits. If it is 0, it would be 0000. Okay. 4 zeros. So here you have to convert. If this is number 10. So 10 means 2 and 8. So I have to put here 1 and 2, 1 and 8. So this is the digit. That's it. And then put everything together. It's just, this is the opposite of what I did before. So what I did before, you have to make group of 4, and every 4 you have to represent it using 1 digit. Now again, I'm going to do the opposite. If I give you hexadecimal, what you have to do, every digit you have to convert it to 4 bits, equivalent 4 bits, okay? And 4 bits should be enough because in hexadecimal we have up to F. F should be 4 bits, should be enough for F, okay? I give you another example here. I'm gonna leave it to you. It's the same thing, 4 and 3, F and 5. Same thing for the decimal point. So this one is 4 bits and this one is 4 bits, that's it. For octal, okay, it's exactly same thing, okay? However, in octal, instead of 4 bits, it's enough to have 3 bits to represent every digit, okay? I think most of the time we only use hexadecimal, not octal, but anyway, but it's exactly same thing, but instead, because you remember in octal, we have number from 0 to 7. So 3 bits should be enough to represent number from 0 to 7, okay? So here, 3 bits here, 3 bits here, 3 bits here. So everything else is similar to what I explained before, exactly same thing. And instead of making groups of 4, now you have to make group of 3, okay? So for example, here, if I want to octal to binary, okay? So every digit here has to be converted to group of 3, not 4, okay? So 5, this one is 5, 1, 0, 1, because this is 1, 2, and 4. 4 plus 1 is 5, okay? This is 4, this is 3, and then put everything together, very easy. Same thing here for the decimal point. This is 4, 3, this one is 3. What comes after this one? 3, 3, 3. So every digit, that's why this one is easier than binary, because it's shorter representation. If every 3 bits represented by 1 digit, okay? Okay, so here I want to convert binary to octal, exactly same thing as hexadecimal. You need to make groups, but this time you have to make group of 3, not 4. So you have to go this way here and this way here. You have to make group of 4. If the last one here is not, you have to make group of 3. If the last one here is not 3, you just add 0 here, okay? So here 1, 1, 1 is 7, okay? 1, 0, 0 is 5. 1, 0, 1 is 2, and so on, okay? Any questions? Okay. Okay, so now I'm gonna explain how can you add binary numbers. I'm gonna focus here more on binary numbers. How can we add binary numbers, and how can we multiply binary numbers together? Instead, for sure here, I don't mean we're gonna convert it to decimal and do the addition and return it back to binary. No, I'm gonna do addition without conversion while they are in binary. Okay, so the idea here, what we do is, you may be familiar with this one. If you add 0 plus 0, okay, if you add bit 0 plus bit 0, the result is 0. If you add 0 plus 1, the result is 1. If you add 1 plus 0, actually the result is 1. However, if you add 1 plus 1, okay, 1 plus 1, the result is 2. Okay, but wait a second. We don't have 2 here, because it's binary. You have only 0 or 1. So actually the result is 1, and then you are gonna move a carry to the next one, 1. So there is a carry here. Same thing if you add 1 plus 1 plus 1, okay? I'm gonna do it slowly, but in the future you should know 1 plus 1 plus 1 is 1, and there is a carry of 1. But let's do it slowly. 1 plus 1 is 0, and there is a carry here of 1 to the next one. 0 plus 1 is actually 1. You get what I'm saying? So conclusion, the conclusion is 0, 0 plus 0 is 0, and there is no carry. 1 plus 0 or 0 plus 1 is actually 1, no carry. 1 plus 1, we have 0, okay, and we have carry. 1 plus 1 plus 1 is actually 1, and we have carry, okay? By the way, this is not very different from the decimal numbers. For example, here, when you add 1 plus 1, here, 1 plus 1 is 2, but we don't have 2, right? So that's why I'm going to make it 0, and then I'm going to move 1 to the next one, okay? Because the weight of this one will be 2, okay? But anyway, same thing, we do the same thing in decimal, by the way. For example, if I add 9 plus 2, 9 plus 2, 11, but we do, or maybe you have some numbers here, other numbers here. We don't say 9 plus 2 is 11. We don't do that, right? 9 plus 2 is 11, but I put here 1, and then the 10, I'm going to move a 10 here by 1 because the base is 10. But anyway, it's the same thing here. The base is 2. So if I have 2, okay, so I'm going to, and it's the same thing for 1 plus 1 plus 1. 1 plus 1 plus 1 is 3, right? But we don't have 3 here. So I'm going to move 2 here as 1, and then the result, the remainder here is 1. But anyway, the way, whatever you understand, the way you understand it, it's totally fine. But again, I just want to tell you it's not different from the decimal numbers, okay? But again, you need to know this one because that's what we are going to use it all the time, okay? So what you have to do here when you do the addition, first of all, you have to start right to left, okay? And this is similar, to the decimal numbers. When you add decimal number, you start right to left, okay? You here you have to do right to left, and then as we see here, 1 plus 1 is 0, and there is a carry here, okay? So now 1 plus 0 plus 1, 1 plus 0 is 1, right? And then 1 plus 1 is 0, and there is a carry here. 1 plus 1 plus 1, 1, and then you have a carry here. 1 plus 1 plus 1, okay, should be 1, and we have 1 carry at the very end here, okay? As you will see in this course, we care too much about the carry resulted at the very end. This one is very important to us. You will understand why. Okay, so we may not care much about the internal carries here, but we care about the carry here resulted from the very end here. Okay. Yeah. So here I give you some examples. This should be very easy. So here, if this is number 7 and this is number 21, okay. So if I do the addition, 1 plus 1 is 0, and then we have 1 here, 1 plus 1 is 0, and we have 1 here, 3 ones is 1, and then we have 1 here, 0 plus 1 is 1 here, okay? So if you add this number plus this number plus, this is the result, okay? For sure, if I convert this one to decimal, the result will be correct. So 7 plus 21 is actually 28, okay? Now I'm going to move to multiplication. Okay, so the way we do multiplication, again, it's really funny because it's not different from the way we do the decimal numbers. It's almost the same thing, okay? So if I do multiplication here, as you see here, this is exactly the same thing like decimal numbers. Exactly same thing, look here. So I'm going to take the first one here, I'm going to multiply by this one, by this one, by this one, by this one. That's exactly what we do in the decimal number. So, but you have 1 times 1 is 1. 1 times 0 is 0. 0 times 1 is 0. 0 times 0 is 0. Is that okay? So always you get 0 except if you have 1 times 1. So here 1 times 0 is 0. 1 times 0 is 0. 1 times 1 is 1. 1 times 1 is 1. So now I finished the first digit. I'm going to repeat again for the other digit, but every time you move from one digit to another, you need to shift one digit. Okay, you need to shift one digit. This is exactly the same thing we do in decimal number. So let's see the second one. This is an easy case because this is 0. So 0 multiplied by anything is 0. So I'm going to put here 4 zeros. That's it. So now 1. So 1, that means I'm going to get exactly the same number in 1. So I'm going to put the same number, but every time you have to shift by 1. You have to shift it by one digit, as you see here. The last one here, you have to put it this way. Is that okay? And then I'm going to add here, nothing here, it means zeros, okay? So 0 plus 0 plus 0 is 0. I'm going to just do addition. 0 plus 0 plus 0 plus 0 is 0. 1 plus 0 plus 0 is 1. 1 plus 0 plus 0 plus 0 is 1. 0 plus 1 plus 0 is 1. 1 plus 1 is 0, and then we have 1 here, carry. You do normal addition or binary addition. 1 plus 1, you have 0, and then we have 1 here. Okay, this is the answer. So here I multiplied 4 bits by 4 bits, and the result here was 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. Any questions? Again, it's almost similar to the decimal multiplication. Okay. What's the time now? Now, now I'm going to explain how can we sign the numbers. sign numbers, okay? Because the situation here is somehow different. The way we represent positive and negative numbers in binary is different from the way we do it in decimal numbers, okay? In decimal numbers, for example, you have 37, that's a positive one, or I can put negative 37. So I can just put here one sign to tell me if it is positive or negative. Is that okay? In binary numbers, we don't do this way. Why? Because it's not hardware friendly. Okay, so it's going to be difficult to implement it using the hardware. Okay, so how you are going to do it? Very simple. The way you are going to do it is, okay, if you look, for example, here, 4-bit. If I have a 4-bit number, so these are all the possible cases for 4-bit number. Okay, okay. Let me explain exactly to understand, because this sometimes students are confused here. So in binary number, we are not going to use positive or negative as usually do in decimal numbers. Okay, instead, the whole space you have, the numbers you have, I'm gonna split this number between positive and negative, okay, as you will see. For example, if you have 3-bit numbers, these are all possible cases for 3-bit. I can have something like that. I can have here 1, I can have 2, I can have, I think 3, and then I can have 4. This all combination, different combination. And then you have 5, and then you have 6, and you have 7. So here you have eight different combination here. So what we do now is, okay, so we are gonna split. So I'm not gonna use the whole numbers for positive numbers. Okay, this is in case of signed numbers. So what we do is the numbers that have zeros at the end, I'm going to use it for positive numbers, and the numbers that have ones at the end, I'm going to use it for negative numbers. You got what I'm saying? So, so I'm not going to add positive or negative, but the whole space we have, or space here, I mean all different combination, I'm going to split part for the positive, part for the negative. So what I want to tell you here in this slide is to represent or to make negative numbers, to represent a negative number, there are different approaches. There is approaches called signed magnitude, signed first complement, signed second complement, okay? But I'm not going to teach this approach or this approach. I'm going to only focus on this approach because this approach is very widely used. It's called signed second complement, okay? So in exams and anything, I'm not going to even explain this too, but I just want to tell you there are different approaches, but most of the computers now are using this one. Why? Because this one is more hardware friendly, and you will understand exactly what I mean in this course. You will see how using this approach, I can use the same hardware to do addition and subtraction. I don't need new hardware for subtraction, okay? So that's why it's more efficient to use this approach to represent negative numbers. So here, as I told you, this is the whole space we have for numbers. So every time you see zeros at the end, okay, so you know these are the positive numbers, and once you have ones in the most significant bit here, so these are negative numbers, as you see here. We have negative numbers here and positive numbers here, okay. What I need to teach now is number one, given this number here, how can you convert, or this number? So given this one, how can you know this is -3? Okay. And also the opposite. How can you convert to the opposite? If I tell you, can you make -7, which is this one? How can you do it? Okay. I'm going to tell you how can you make it. Okay. So actually, but before I do that, there is something we call it complement a number. Okay. There is an operation, we call it first complement and second complement. So what this means, okay? First complement and second complement, what this means. I'm going to tell you what it means. For example, let me see any space here, okay? For example, if you have a number like this one, 101010, is that okay? Is this just a number? If I ask you, can you please calculate the first complement of this number? Okay, so first complement means you just flip the bits. So this one should be 0, 1, 0, 1, 0. So you just flip the bits. So this is actually, this one is the complement of first complement of this one, or this one is the first complement this one. Okay. So if I give you a number and I ask you to first to complement the number, all what you have to do just to flip the bits. Is that okay? This is, we call it first complement. The second complement is you take the first complement and then you add 1. So if I add 1 here, 0 plus 1 is 1, and then 1, 0, 1, 0. Okay. So that means from here to here, this is the second complement. From here to here is the second complement. Okay. So very simple. So if I give you a number and I ask you to calculate the first complement, that means you just flip the bits. If I give you a number and ask you to calculate the second complement of this number, number 1, you have to calculate the first complement by flipping the bits, and then when you add 1, you have the second complement of the number. Is that okay? So why I'm explaining this? Simply because if I go here, look here, this is a very interesting part. If you go here, this is positive 7. Is that okay? If you see the relation between positive 7 and negative 7, it's simply the second complement. You got what I'm saying? That means if you have a number and you calculate the second complement of this number, it's you multiply it by negative 1. So if I have 7, and I calculate the second complement, I'm going to get negative 7. If I have a negative 7 and I calculate the second complement, I'm going to get positive 7. Is that okay? So let's do it. For example, if you have 1, 0, 0, 1, okay? I want to calculate the second complement of this one. It's very simple. I told you have to flip the bits, and then you have to add 1. So it should be 1, 1, 1, 0. So actually, so you should understand these two numbers, okay? They have the same number, 7 and 7, but this is a negative version of it, and this is the positive version. Why? Because there is 1 at the end here. You understand what I'm saying? So as you see here, let's have another example just to convince you. For example, here, this is a positive 5. Okay. If you calculate the 2's complement of positive 5, you are going to come here to negative 5. If you calculate the 2's complement of negative 5, you are going to get positive 5. So if you have a number and you calculate the second, or the second or 2's, 2's means 2. It's coming from 2 complement, or the second complement, whatever you call it. Okay. So if you calculate the second complement, okay, or the 2's complement, so actually it's like you multiply by negative 1. So if I have a number x, whatever x is, if I calculate the 2's complement, I'm going to get negative x. If you have negative x, you are going to get x. Okay. So that's okay. That's why here, that's why I'm going to tell you, if I give you a number, how can you convert this number to decimal now? Okay. If this number is signed, okay, what you have to do is that 2 cases. If this number is positive or negative. If this number is positive, at the end there are 0, 0, 0 here, the way you convert it, similar to what I explained before, you have to multiply. So in case of positive numbers, you have to multiply every digit by the weight. So this one, 1, 2, 4. 1 to 4 is 7. Okay. So if I come to this one, 1 and 2 should be 3. Okay. So if the number is positive, okay, so you just convert it similar to what I explained before. You have to multiply every digit by the weight. Okay. Now, if the number is negative number, like this one, okay. So for example, this one, how I can know? I know this number is negative because the most significant bit is 1 here. I know it is negative, but negative what? I don't know, right? How I can know? How I can know if it is negative what? Okay. So what you have to do here is, for sure there are different ways, but to me the easy way, or the way I love to explain it, if you have a negative number, you can simply calculate the 2's complement. When you calculate the 2's complement, you are going to get the positive version of this number, and then you can read it easily. For example, let's see, for example, if you have 1, 1, 0, 1, okay, this number is negative. Okay, please get the positive version of this number. Okay, calculate the 1's complement here, and then add 1. Yeah, so if this one negative x, this one should be positive x. Is that okay? And now, because it's easy for me to do this one, so this number 3, so this should be minus 3. Okay. So again, what I'm saying is that what I'm saying is, if the number is positive, it's easy to convert this number. Just multiply every digit by the weight. Okay. If the number is negative, I can calculate the 2's complement of this number to get the positive number, and then do the conversion of this positive number. You got what I'm saying? Let's have another example here. For example, here, if you have this one here, 1, 1, 1, 1. Okay. So if you have 1, 1, 1, 1, this is a negative number. Okay. So let's get the positive version of this number by calculating the 2's complement. So if I do the 2's complement, so I flip the bits and then add 1. So this one. So that means these two numbers are the same as a magnitude, but this is negative and this is positive, right? Because this is how 2's complement works. Okay. So if this is positive 1, this one should be negative 1. Okay. Let's see what is the time now. Okay. Maybe I'm gonna, because this part may be new and a little bit difficult, so I'm gonna explain it again in the lecture. So yeah, so maybe that's exactly what I'm explaining here. So for example, in exams, if I tell you here, for example, in this example, I have negative number and I want to represent it in 8 bits. Okay. So negative 5. So what you have to do is that, again, this is the easy way in my opinion. Just to make 5. 5 is easy to make positive 5. Okay. It's easy to convert to positive numbers. So do the positive number and then calculate the 2's complement. Okay. So let's start with positive 5. So positive 5 actually is, here you have 1 here. Okay. And then you have 0, 1, 0, and then you have 0, 0, 0. Why? The weight of this one is 1, 2, and 4. 4 plus 1 is 5. Okay. So you have 1, 0, 1, 0, 0, 0, 8 bits. These are 8 bits. So this is positive 5 in 8 bits. Okay. Now, if I calculate the 2's complement of this one, I'm going to get negative 5. Okay. So let's do it. So it's going to be 0, 1, 0, 0. Oh, I'm sorry. 0, 1, 0, 1, and then 1, 1, 1, 1, and then add 1. So this number is actually negative 5. So in exams, on anything, if I ask you to convert, for example, negative 7, okay, it's easy to start with 7. Okay, it's easy to make 7, and then you can calculate the 2's complement of the 7 to get negative 7. It's the same thing. If I give you this number, which is a negative number, it's easy to convert it to a positive number, and then it's easy to convert this one to decimal and then add minus. So anyway, just to finish this one, and then I'm going to do it in lectures. I'm going to explain again in lectures because this is somehow new to most of the students. Quantity, when you have, like, when you do programming, sometimes you have signed numbers, you have unsigned numbers. So sometimes the quantity, something you are measuring, the quantity of it is signed or unsigned. For example, if I want to calculate the number of students enrolled in this course, for sure, this is unsigned number. Unsigned number means it's 0 or positive. It can be negative. Number of cars, number of students, all these numbers, they 0 or positive, they can be negative. Okay. But when I come to other quantities like temperature can be positive or it can be negative. So now, same thing here. If I have a number, I'm going to decide if this number should be signed or it is unsigned. Okay, signed or unsigned. If signed, so this number is going to be only 0 and positive. So let me tell you here. For example, here, if number of bits are 3, so these are all the combination I have. There is a relation between number of combination and the number of bits. The combination 2 to the power of n. So here you have 3 bits, right? So how many different combination I can get out of 3 bits? 2 to the power of 3, which is 8. How many different combination I can get if the number is 4 bits? 2 to the power of 4, which are 16. These are all possible cases. What if the number of bits is 5? So 2 to the power of 5, which is 32. Is that okay? These are all the combination, possible combination for this number. So let me tell you something important now, okay? What happens is that If this number is unsigned, so I'm going to use the whole space. I'm going to use the whole combination in the positive side. Okay, so that's why this one can go from 0 up to number 7. So from 0 to 7, because I'm going to use the whole space in the positive side. However, if this number is signed, so I'm gonna cut it into half, because half is positive and half is negative. Okay, so now I'm gonna give you rules. Okay, the rules are: number 1, if you have any bit number, how many combination you have? 2 to the power of n. Okay, we know that. If your number is unsigned, that means in n bits, I can represent a number from 0 until 2 to the n minus 1. In this example, 2 to the power of 3 is 8. So 8, you can represent a number from 0 until 7, because I'm going to use the whole space in the positive side. So in general, it's from 0. So I'm going to use one combination here, or one number for 0, and all the other numbers, I'm going to go all the way until 2 to the power of n minus 1. Total number 2 to the power of n, total. Okay. However, if this one is signed, I'm going to use half in positive, half in negative. But actually, it cannot be exactly half. Why? Because this is 8, right? This is 8. Because we have 0 in the middle. So you understand what I'm saying? So you have 0. So it cannot be exactly half and half. So positive should be greater than negative, or negative. What happens here is actually negative is greater than positive. So this one, it can be from -3 to +2. Okay. Sorry, +3. I'm sorry, +3 until -4. I'm going to give you the formula right now. So if you see how many numbers you have, you are going to get 8 numbers. They are not equal because there is 0 in the middle. I can't cut exactly in half. Okay. So in general, if you have a signed number, you can go from -2 to the power of n minus 1, which is exactly half. Okay. 4 is half of 8, until 2 to the power of n minus 1, and then we have here -1. Okay. Remember, the half is 2 to the power of n minus 1. This is half. Okay. So here for negative, I'm going to go to the half of the 8. Okay. But this one has to be -1, because we have a 0 here. But anyway, I'm going to continue teaching this one next time. I think that's enough for today. Thanks.